Welcome to our bonding revision video. In this video we're going to be just revising some of our work on metallic, ionic and covalent bonds. Now before we can start that, we just need a reminder of the periodic table, okay, and that arrangement of the periodic table. So we've got two diagrams here of the first 20 elements from the periodic table. I keep saying periodic table, sorry. Well, on this one, the first 18, here we've got the first 20. When we look at this, you can see those different arrangements. For example, all of these elements in group 1 all have one electron in their outermost shell, okay? And you can see that when you look here. So hydrogen with its one electron. Then we've got lithium, and lithium's got two electrons in the inner shell, one on the outer in its valence shell, so the outer shell. Sodium's got 2 in its central shell, 8 in its next shell, and 1 in its valence shell. So all the elements in that group 1 have got one electron in their outer shell, okay? And that's going to come to play quite importantly as we look at some of our bonding types. Sorry, I said 2 there because we're looking at metals, except for hydrogen. Looking at metals there, and that only applies to 2 types of bonding. Now, so if we look down the second group, we can see they've got 2 electrons in their valence shell. And then group 13, just remembering there's some complications to the old periodic table because we've got those transition metals that aren't here. Okay, so we've skipped up to group 13 here, and we've got 3 electrons in the outer shell. We've got group 14 here where we've got 4 electrons in the outer shell, nitrogen, well, it is nitrogen, but group 15 with 5 electrons in the outer shell, and so on. Now, going across what's known as the periods, we've got what's in common here is they've all got 2 shells, okay? So 1, 2, 1, 2, 1, 2, 1, 2. Going across here, what's in common, they've all got 3 shells. So it's just, you've already seen a lot of work around the periodic table. This is just a reminder. It's more importantly about that valence shell as we move through our types of bonding. Okay, we need to get our minds into this sort of ions for some of these bonding types. And that is, we start off with our neutral atoms as we just saw on those diagrams of the periodic table. Now, our neutral atom can gain or lose electrons depending on how many electrons it's got in its valence shell and whether it's a metal or a non-metal as such. We'll get into that as we go through. But a neutron that loses electrons becomes a cation because it has more protons than electrons, so it's positive, okay? So our cation is positive. A neutral atom that gains electrons becomes negative because it's got more electrons than protons, okay? Electrons being negative. So it gets this negative charge, and our cation, because it's lost electrons, has this positive charge. This is important as we look at metallic and ionic bonding. Okay, so still thinking along that line, we're just going to think of our cations, and these are generally our metals, okay? Now, what happens with our cations, as you can see with sodium here, in our neutral atom, it's got 11 protons, 11 electrons, so 11 protons in the central, 11 electrons in the electronic shells. Now, if we look at its valence shell, it's only got 1 electron, valence shell being that outer shell. So what happens is sodium likes to have a full outer shell, okay, and our metals like to have a full outer shell. So in the case of sodium, it needs to lose its valence electron from there. So it loses that one electron from that outer shell. It's now happy because it's got a full outer shell, so it's not so reactive. However, it's got a charge now because it's got 11 protons and only 10 electrons. Protons being positive, it's now got more protons than electrons, so it's got a charge, it's got a positive charge, and because it's lost one electron, it's just got the +1 charge. Got some examples here of sodium, so that +1 charge on the cation, and then we've got chlorine, which is an anion. Okay, so chlorine actually loses an electron, so we'll get to anions next. Okay, so we just talked about chlorine and we saw that it lost an electron. Okay, now we've got another example here. We saw that chlorine gained an electron. We've got another example here. We've got oxygen. Okay, now as you can see, oxygen's got 6 electrons in its outer shell. It wants to make a full outer shell, okay? So it's going to gain 2 more electrons. And by gaining 2 electrons, it's now got 2 extra negative charges. Okay, so our oxygen then becomes negatively charged. If I just go back to look at chlorine. Okay, so our chlorine gained an electron, so that's why it then got the negative charge. Here it had an equal number of protons and electrons. Here it's gained that electron. The electron's having a negative charge, so it got its negative charge. Okay, so in your information pack in your exam, or in your exam paper somewhere there, you will get this, the valency of common ions. And this is showing you that in terms of all of these elements, they have this valency of +1. Okay, so they have lost 1 electron from their outer shell. Here they've lost 2 electrons, here they've lost 3 electrons. And the reason they've lost them is so that they can then use that shell beneath. That is a full shell. Okay, hydrogen's a little bit different. Hydrogen is always a bit different because it's not actually a metal to start off with, and the way it behaves is a bit unique. Okay, but all of these, so lost 2 electrons, lost 3 electrons. Just remembering things like iron, so quite a few of the transition metals can come in different forms as such. You've got iron 2 or iron 3, you've got copper 1, copper 2. You'll generally be told which you're using if you're using one of them. Over here we've got our anions. So we've gained an electron. Here we've gained 2 electrons, and here we've gained 3 electrons. Okay, now these tables will come important when we start naming ionic compounds. Okay, so we are going to start looking at our 3 types of bond, and we have our metallic bonds, and as you can see here, we've got these delocalized electrons floating around between our cations, our metal cations. We've got our ionic bonds, and what happens with our ionic bonds is a metal gives away its valence electron or electrons to a non-metal, then the metal ion becomes positively charged, the non-metal becomes negatively charged, and there's a force of attraction between them, that static attraction between them, so they are bonded. And then we have our covalent bonds, which are between non-metals and non-metals, and this involves these 2 atoms sharing electrons. We'll look at each one in a little more depth and some of the properties of them. Starting with metallic bonding. Okay, so as I said, with the metallic bonding, we've got our cations here with their positive charge. Okay, so they've lost an electron. They've now got one or more protons compared to electrons. And surrounding them is all those electrons that they have actually lost in this delocalized sea of electrons. So it kind of looks like this. We've got all our positive cations with our electrons all around. Now, what we're going to do is we're going to look at an explanation of the properties of metals in terms of that metallic model. So in terms of them having all those delocalized electrons. Okay, so metals are good conductors of electricity, and this is because those delocalized electrons will carry that electric charge from the negative to the positive end, so causing electric current. They're good conductors of heat, for a similar way. As those particles get hot, they move faster, and this allows that energy to bump along the metal as such. The particles move and move faster and faster, transferring that energy along. Now, luster, that's that appearance of the metal, that shininess, and it's due to the delocalized electrons being able to reflect light. We've got malleability and ductility. This is where metals can bend and be hammered into shape, and it's all because of those non-directional forces between the electrons and the cations, which means it's not fixed into a lattice structure as such, into a strong lattice structure, so it can be bent and moved. Our metals have high boiling points and are hard, and this just is due to that really strong bonding. Okay, a substance with a low boiling point has weak bonds in it, whereas our metals have very strong bonds, so they have relatively high melting points, other than, of course, mercury. And finally at the bottom there, sorry, it's a bit cut off, is high density. The reason metals are quite heavy, have that high density, is because their structures, those lattices, are quite closely packed. So there's quite a lot of particles in a set space, making that high density. All right, we move on to our ionic bonding now. And our ionic bonding is between a metal and a non-metal. In this case here, we're looking at sodium that wants to give away that valence electron, and we're looking at chlorine that needs to gain one electron, okay, because that's got 7 in its valence shell. It needs to gain one, and sodium wants to give one away. So chlorine gains an electron from sodium to fill that valence shell, but now has a negative charge. Sodium has given away an electron, but now has a positive charge. And now, because it's a positive and a negative charge, there's this static force between them that holds them together, and hence they are bonded. This only occurs between metals and non-metals. Here we've got magnesium, and magnesium has got 2 electrons in its valence shell, which it needs to get rid of. Now, with chlorine, chlorine still only needs to gain 1 electron. So what's going to happen is 2 chlorine atoms are going to come along, and those 2 electrons are going to split 1 to 1 chlorine atom, 1 to the other, and then we get our magnesium chloride, which with magnesium will always be in the middle because everything needs to be balanced in chemistry. So there'll be a chlorine on either side with magnesium in the middle. Alrighty, now ionic structures also have certain properties, and it's due to the ionic structure that they have these properties. That didn't make much sense, but now ionic compounds form crystalline structures, okay, and this is because they're very ordered in their lattice shape. So like I just said, magnesium and the 2 chlorines on either side, they form this really strong lattice, and that's what caused the crystalline shapes. They generally have high melting and boiling points. Again, that's due to those really strong forces between the ions. They don't conduct electricity in the solid state. Okay, this is because they've not got the free electrons moving between them. They have hard surfaces, they're difficult to scratch. Okay, again, this is because of those really, really strong bonds. They are water soluble, okay, and this is because they are polar molecules, okay, which means water is able to get between the two. So imagine you've got a sodium and a chlorine. Water gets between them and kind of splits them apart to a certain extent. Okay, so it applies to most salts, but not all of them. Now, a salt is a metal and a non-metal bonded, your ionic compound. So if you hear the word salt, it doesn't just mean table salt. Ionic compounds can conduct electricity when in liquid states, so either molten or in solution. Okay, and that's because the ions are then disassociated from that lattice and can move freely about, conducting electricity. We call ionic solutions electrolytes. And then finally, ionic compounds are quite brittle. They break easily. Okay, this is because of there's the positive and negative charge, and they're in a fixed arrangement, but they can move and start repelling each other. So it just means they'll shatter easily. Again, I've just brought up the valency table to remind you when we're looking at ionic compounds, the number of electrons in those valence shells that they're going to gain or give away. You have that in your exam. It's just important that you know how to read it. Now, the reason that I've put it there, excuse that scribble, but steps for writing ionic formulae. Now, here we are going to be looking at aluminium oxide. But to get to aluminium oxide and know how many aluminium atoms there will be and how many oxygen atoms to make aluminium oxide, we've got a few steps. So first of all, we write the cation and make sure we've got its electrovalence. So there we've got its electrovalence. It's a 3+. Now, if I go back, I can't do this each time, but look on here, aluminium is 3+. It's got 3 electrons it's going to want to get rid of. All right, then we write our anion. Okay, and in this case, we're looking at oxygen. Oxygen has 2 electrons it wants to gain. So we write the 2 of them together. Okay, and we're doing what we call swap and drop. So the 3+ is going to come down here next to the oxygen. The -2 is going to come across here. We get rid of the charge. Okay, so the plus and the minus, we get rid of them. And we write our full thing out like this. So Al2O3, and that's because we've done that swap and drop. We now know we need 2 aluminium ions to bond with 3 oxygen ions to make aluminium oxide. All right, when we name our ionic compounds, we have some rules to follow, okay? The cation always is written first, and the net charge of our compound must be 0. So we write the cation, then the anion, and we must make sure that net charge is 0. We do that by that swap and drop. Now, most ionic compounds have 2-word names. The best way to approach this is naming an ionic compound is to look at that formula. So if you add Al and O, you know it's aluminium oxide. Now, the ending of those names are a bit tricky, but we'll get to the endings in a minute. First of all, we just need to remember that if they're in the group A, the cation is just a name. So, for example, sodium is a sodium ion. Okay, if we're dealing with transition metals, we just need to double check what form we've got. So for example, iron can be the +2 or the +3. You remember we had copper that was +1 and +2 earlier. You'll always either be told that or be able to work that out. All right, when we name our anions, sorry, it's the anions with the endings. I got a bit confused back there. When naming anions with only one atom in it, then we just change the ending to an "ide." So, for example, oxygen becomes oxide. It's only got oxygen in the anion. Sulfur, sulfide. It's only got sulfur in the anion, and so on. So, chloride, sulfide, fluoride, only the element named is in it. However, so bonded them with the metal, so we've got sodium nitride, which is sodium and only nitrogen. So ides are the element alone. If we have ide, one element alone, we said that. If we've got 8, so ATE, this tells us that there's more than one element in the ion, and that one element will always be oxygen. Okay, so if it's ide, it's only one element. Sulfide is just sulfur. If it's got 8, we know that it's got oxygen in it, so carbon 8. Now, carbon, anything with 8s have more oxygen than ites. Okay, so if we look at hydrogen sulfate here, it's got 4 oxygens, whereas hydrogen sulfite only has 3. Okay, so ites have 1 less oxygen than 8s. Okay, again looking at our 8s and our ites, we've got sulfate here and sulfite here. So our ites have 1 less oxygen. And finally, we're going to have a look now at covalent bonding. All right, covalent bonding occurs between atoms of non-metals. So we've got our chlorine and our chlorine here, and what they're going to end up doing is sharing those 2 electrons, because they've both got 7 in the outer shell and they want to get a full shell of the 8, so they share 2 electrons. Now, when we look at covalent bonding, we have an intramolecular force, which is that covalent bond we just looked at there with the 2 chlorines, okay, where they're sharing electrons. But due to the positive negative nature of these ions, you also get these very, very weak intermolecular forces. So in our gases, if our covalent molecules are in gaseous form, these forces are broken or very, very rare, whereas in water there would be, in liquid form there would be more of these forces, okay, and they're just weak intermolecular forces. So when we've got covalent compounds, we quite often draw them as electron dot diagrams. So rather than drawing them like these with all the valence shells and dots, what we do is we just draw the valence shell. So we write the chemical symbol, so this is chlorine, and then we've put the dots around representing the valence shell. This means that it's much easier to draw diagrams with bonding, covalent bonding involved, because we're only drawing those that valence shell. So here we've got chlorine bonding with chlorine again. this diagram is showing us that the bonding electrons, that bonding pair there, and any non-bonding electrons around it you'll see are in their lone pairs, so they're not involved in the bond at all. Okay, two different diagrams here. So these electron dot diagrams can also be called Lewis diagrams. And above that, we've got what we call a structural diagram, where one line represents two electrons. So we've got two electrons here being shared. One line represents two electrons. Okay, we've got oxygen bonded in its molecule here, that O2 molecule. And you've got a double bond here. Okay, so we've got a double bond between the oxygen atoms, and that line represents two electrons, remember. Here we've got nitrogen bonding with another nitrogen atom, so N2, and because there's only 5 electrons in the outer shell here, it wants to get to 8, so 5, 6, 7, 8. They need to share 3 electrons each to fill their outer shell. A triple bond is much stronger than a single bond in covalent bonds. This table you'll get in your exam, this is just showing a range of anions, the cations that they can potentially bond to, and whether they're soluble or not. So if you are writing out an equation, and for example you have got potassium phosphate, you'll know potassium phosphate is soluble, so you would put the little AQ there. If you had calcium sulfate, it's got a low solubility, but it is still soluble. I hope you found that video helpful and enjoy bonding.